Thank you for joining this webinar organized by Physical Acoustics Group of UCAM Plus Network. Our speaker today is Dr. Marina Terzi of Le Mans University, Acoustics Laboratory of Le Mans University. And her talk is about directed motion of particles on vibrating substrates. Dr. Terzi got her undergraduate and master's degrees from Moscow State University and her PhD from University Hauts-de-France. Her research is on particle motions on vibrating surfaces, and which has applications in industry regarding microcleaning and other applications. What the plan of the talk is that she will give her talk, and then if you have any questions, I'll be grateful if you could wait until the end of the talk, and then I'll ask for all the questions at the end. So without further ado, I'll hand over the virtual microphone to Dr. Terzi and welcome her to our session. Thank you.
Hello, hello everyone. Can you hear me well?
Yes, we can.
Yes, good. I would like to thank UCAN Plus organization for inviting me to this talk. That was quite surprising. So today I'm going to talk about the directed drift of a deformable axisymmetric particle on a vibrating substrate. I work in Laboratory of Acoustics in Le Mans in France, and we collaborate with University of Lille, also in France. So yeah, we're going to talk about vibrational transport, and this is based on the phenomenon when solid objects can move on dry vibrating surfaces in a specific direction. And since there is a preferable direction, it means that there was some asymmetry in the system. It could be different sorts of asymmetry. For example, asymmetric vibrations, as you can see on the slide, it's applied in conveyors or shaken chutes and the table when the vibration is applied at a certain angle, and that's how they transport food or medical powders. And the other type of asymmetry is asymmetric friction that we are going to be focused on today. One of the ways to achieve this kind of asymmetry is to excite an acoustic wave in a substrate. And if a substrate is significantly thick comparing to the wavelengths, it's most probably should be the Rayleigh wave, as you can see on the picture. And if we pose an object on this substrate under certain wave parameters, the drift might occur. So the slow motion in the particular direction. And yes, as you can see, friction is indeed asymmetrical with respect to 0, so between left and right. And this is because the wave is periodic, which means that the normal force, normal load at the contact spot between the particle we posed on the substrate and the substrate itself is also periodic, so it's changing in time. And the Coulomb's law which is a relation between friction force and the normal force, it's also applied differently at every given moment of time, at every given phase of the wave. Sometimes a tangential force equals mu times normal force, which is a condition for sliding, for drift. But sometimes it's not. When the red and blue curve corresponds, it's sliding. When they don't, it's something else, which is to be discussed in this talk in greater detail later. So this drift, this vibrational transport, could be applied for micropositioning when we need to put something in a precise place. It could be also applied for activating micro devices or robots that are that small that it's impossible to put a motor inside them. And if we excite acoustic wave, maybe they will move the way they should. Also, if we have a mixture of particles of different masses or made of different materials in general, under certain conditions, if we excite acoustic wave, they might move in different directions. The sort 1 to the left, sort 2 to the right. And this is a way to separate dry mixtures. And the last application I'd mention is cleaning surfaces like dust removal without water. So for example, in deserts, we have solar panels which are subjected to a lot of dust, and when dust occurs, their functioning is gravely inhibited. The efficiency is lower. So if we could clean those surfaces without water, like by shaking them with vibrations, that would be cool. So to obtain this drift, what should we do? We excite wave, but what kind of wave, with what parameters, and in what direction the particle is going to move? Let's find out. The simplest model of this process is a material point model. So we have a particle that has no size, no shape, posed on the substrate where Rayleigh wave is excited. The forces that act on a particle are gravity, friction, and normal reaction force. And then the sliding or drift condition would consist of two conditions. The first one is Coulomb's law, so that the tangential force should be greater or equal to mu times normal force, and that the normal force should be greater than 0. The second condition corresponds to the fact, sorry, that the particle does not detach from the surface, so that gravity is greater than the normal component of wave that is trying to detach particle from the surface. So it stays on the surface and it slides along it. This is the drift we are looking at. And then if we solve these two conditions together, we have the inequality drift condition. So this is kind of dimensionless acceleration between the wave and the gravity. And it depends on friction coefficient, mu, and the wave polarization, beta, the ratio between horizontal and vertical components of the wave. And graphically, we can represent this inequality with something we call phase diagram. We have frequency against vertical amplitude of the wave on the graph. And here, the red strip, the red area corresponds to the sliding drift behavior. If we go below this strip, in frequency. And then there is no motion. The particle sticks to the substrate. And above this strip, the particle detaches from the substrate and starts bouncing, jumping on the substrate. Another prediction of this model is that drift is only predicted in the direction of the wave propagation. So the particle moves in the same direction as the wave does. This is a red color on the diagram. But is it the case in the reality? Do particles move only in the direction of the wave, or they could move otherwise? What if we take into account normal deformability of the particle? Before, the particle was absolutely rigid. In this case, Hertz solved this problem of a sphere compressed against the half space in 19th century. So it's called Hertz on contact. And if a sphere is subjected to normal force N, and then its center of gravity is displaced by 2a. A is the displacement, normal displacement. Then the relationship between this force and displacement is N is proportional to a to the power of 3 over 2. So it's a nonlinear link. And the proportionality coefficient depends on the elastic properties of sphere and the substrate, as well as the sphere's radius. Static contact compression A0 is a displacement when N equals gravity. And it appears that the dynamics of this system is very different comparing to material point system. There is a contact resonance frequency, omega c, at which if we excite wave at this frequency, even at very low amplitudes, sphere will start jumping and there will be no drift, only jumping directly. So this is not what we want. And if we go to frequencies much lower than this contact resonance frequency, then contact deflections, contact deformability can be neglected. It's a long wavelength approximation. The surface could be almost considered flat for the particle. And in this case, more or less, we can apply the material point model that we used before. But if we are around the contact resonance frequency or above it, then contact deflections must be considered, and the surface is quite wavy. So we need a model that would consider the deformability of the particle and explain the motion against the wave. So here we also take into account tangential deformability. In this case, if two spheres are compressed against each other at oblique angle, it's called Hertz-Mindlin solution for relationship between force and displacement. And what's interesting that a contact between spheres consists of stick zone, the blue one, and slip zone, the red one. And the stick zone doesn't move, and the slip zone, the spheres slide against each other. And the tangential force displacement relationship depends on this size of the contact zone and the stick zone, C and S. So yes, we know the solution for very simple load. A and B are normal and tangential displacements, and here they are linear or constant. If we go to more complicated displacement histories, in this case, my co-author Vladislav Aleshin proposed a method of memory diagrams, which is a semi-analytical generalization of Hertz-Mindlin solution. So as an input to this system, we give displacement history A and B as a function of time. And as an output, it computes stresses or forces as a function of time. And here you can see stick-slip zone evolving during this excitation. And on the right, there is a tangential force as a function of displacement. And this works for any two axisymmetric bodies, not only spheres, and arbitrary histories of displacements. And I forgot to mention that stick and slip coexisting as a contact is called partial slip. But when the slip takes all the contact zone, it's full sliding. So both of these regimes are taken into account in this model. Means for given wave type, like Rayleigh wave, and the particle shape implies the normal force displacement relationship. We can compute tangential force as a function of both displacements and their histories. And then we can apply this method of memory diagrams to solve the dynamics problem of a deformable particle on a substrate where a Rayleigh wave is excited. So yes, here on the horizontal axis, we have only a tangential force computed from method of memory diagrams. And on the vertical axis, we have gravity and normal force that comes from the shape of the particle. Here it would be sphere. And then we excite Rayleigh wave. And the motion consists of two parts. It's part of the wave and the part that comes from the contact as a reaction to this wave. If you will, it's a motion in the reference frame associated with the substrate. Or in coordinate form, it's wave plus A for normal component or B for tangential. A and B are normal and tangential displacement in this reference frame of the substrate. And we assume 0 initial conditions. And for this, we multiply our Rayleigh wave by ramp function, meaning that it starts from 0 and then we turn it on gradually. Also, we neglect kx term because we assume that the tangential displacement per period of the particle will be much less than the wavelengths. And what's important here is that we think that nonlinearity of the contact between sphere and the substrate is quite weak, meaning that the wave component of motion affects the contact component, but not the other way around. There is no secondary field or nothing like that. So then we solve this problem for normalized variables, which you can see on the slide. For example, time is normalized by wave frequency and amplitude is normalized by the static contact compression. And the forces are normalized by the gravity force. And then it appears that there are only two principal parameters of this problem, M star and AY star, apart from the parameters related to the materials, Poisson ratio and friction coefficient, as well as Young's modulus. So we have only two principal problem parameters, meaning that we can also represent our solution later graphically as a phase diagram, the same as we did with material point. So we will be able to compare them. First, let's see the motion regimes that occur in this model. The first one is drift against the wave. So what we observed experimentally, this model can explain. So how this drift looks like, we have x, the horizontal coordinate, as a function of time, decreasing drastically at hundreds of units here. So it looks linear at first, but if we zoom in, it's not. It consists of advancing and receding phases of the particle. And on the right, we have a fragment of this curve for 2 periods. We have in red, we have normal coordinate and displacement. In blue is tangential coordinate and displacement. And the hollow points correspond to partial slip, and the full points, field points, are to total sliding. So we can see that when the normal displacement is low, it means the contact is not compressed much. It's compressed the least, the particle is kind of relaxed, it's ready to move somewhere. We see that the total sliding, the field blue points occur and particle advances at low normal compression. And when compression becomes high, we observe hollow points. It's partial slip, which is not that efficient of a motion. And this is receding phase. So we recede less efficiently than we advance. And this is why in average, we advance. And in this case, we advance to the negative direction against the wave. So yes, and also there is a similar regime drift with the wave. In this case, it's very similar, but we have x coordinate advancing positively, also hundreds of units in 500 wave periods, and also advancing and receding phases. And the same, here we can see that at the low compression, when A is small, we see the field points, so full sliding and advancing in the positive direction, whereas when the normal compression is high, we see the partial slip, the hollow points, and receding, so moving to another direction, but less efficiently. So in average, we move to the positive direction. And what's important here also that the amplitude of A of the normal displacement is quite large. So the drift is efficient. And how does the particle choose the drift direction? How does it know where to go? Actually, we have the Coulomb's law, So T equals mu n and signum of the velocity, of the horizontal velocity. And another condition is no jumping, meaning that n is always positive, which means that the sign of the velocity is determined by the sign of the tangential force at the beginning of the drift. So we can see on the graphs that when the red curve, the normal force is low, is small when we are at low compression. On the left graph, the T, the tangential force, is negative. So meaning that velocity should be negative and the particle moves against the wave. Whereas on the right, at the low compression phase, when n is small, a T is oh, sorry, I put the same graph. That's a mistake. Well, here T should be positive. Sorry for that. And if T is positive, then particle moves with the wave. So the drift direction is determined by tangential force in the low compression phase. But drift doesn't occur all the time. For example, let's consider a light particle when m star parameter is very small. In this case, we observe weak oscillations. So there is no drift. The x, the blue curve is oscillating around 0, the same as the tangential displacement B, and does not advance neither to the left nor to the right. And on the right, the fragment of 2 periods for normal and tangential displacement and coordinates shows us that the normal displacement changes quite weakly. The A amplitude is quite small. So there is not enough modulation, or whatever you call it, to inject into the system to move a particle anywhere. So there is no drift in this case. And in other case, also weak oscillation, maybe also weak drift. It's very heavy particle. When m star is quite large, 1000 here, we see that there is a drift, x decreasing, but it's decreasing by 0.8 or 1, whereas in the real drifts, we've seen hundreds of units of decrease. So it's very, very slow and mostly oscillating. So on the right, we can see that here, despite the normal displacement has quite high amplitude of oscillation, but at the low compression phase, when A is small, there is a partial slip, hollow points, so no efficient motion. And it means that the phasing between the tangential and normal components is bad in this case. They are not synchronized for motion to occur. So yeah, despite you can see the green light here. So for low normal compression, it's a green light when the motion can occur. There is no drift, no sliding. There are sliding points, couple of points per period, which is very small. And this is why there is still a very slow drift, but it's just 2 points. And at high normal compression, it's red light because the particle is compressed a lot, it can't really move. So in this case, they're not well synchronized and there is no drift. And as we said, the normal solution suggests an opportunity at the low compression phase. At high compression phase, there is no opportunity for particle to drift. And then it depends on the tangential solution. It's its turn to play. And when it comes to play, it can take the opportunity or not. So that's the game in a nutshell for the drift. And we should absolutely avoid the last regime of motion, which is unstable bouncing. In this case, we see that A, the normal displacement becomes negative. So there is unstable jumping. If we change initial conditions a little bit, the solution changes drastically. So both A and B, a normal and tangential component of the motion, are quite unstable and uncontrollable in this case. So it's not desirable for particle manipulation. These regimes must be avoided. And here are the phase diagrams. So on the left is our deformable particle, and on the right, material point. And here the phase diagrams are in terms of our dimensionless parameters, m star and ay star. And what can we say? First of all, what is the difference between left and right is that on the left, we see yellow areas corresponding to motion against the wave that are absent on the right picture. So motion against the wave can be only explained with deformable particle model. The first thing. Second thing is that we can see the resonance behavior for the green area corresponding to jumping area, jumping motion. And the biggest resonance is here. It's at M star equal M star contact resonance. And in this case, even at very low amplitudes, there is no motion. It's still green. It's jumping. There is no drift. It's jumping. It's jumping. And this contact resonance, as mentioned before, is dividing the graph, the phase diagram into two regimes. When M star is much lower than contact resonance, we're in low frequency light mass regime, because M star is proportional to square of frequency, but it's also proportional to A0, including mass. So a low M star means low frequency and or light mass of the particle. In this case, the particle has time to react to the wave, and it prefers moving rather than deforming according to the wave. And we can neglect the deformability, and the material point model works quite well. Here are the fragments of the diagrams at very low M star. On the left, deformable particle, on the right, material point. We can see that the diagrams look similar, except for the drift direction. On the left, we have yellow strip. On the right, there is no yellow strip. On the right, it's only with the wave. And if M star is greater than contact resonance, then we are in high frequency heavy mass regime. So in this case, the particle is too lazy, or the wave is too fast. So the particle has no time to react to it, and it prefers deforming rather than moving. And in this case, deformations are important to take into account, and this is this area of the diagram on the top, where we have motion against the wave and jumping, but which is absent on the material point diagram. And also the third thing is that for deformable particle at the very low amplitudes, there is no motion at all, which is logical. But the rigid material point moves all the time. This red strip goes to minus and plus infinity. So deformability helps you take into account this as well. And then we can convert this phase diagram into physical quantities, frequency and amplitude, for a particle of a certain size and with particular materials. So here's example for 1 centimeter here. And we can predict the drift zones at particular frequency and amplitude. So the motion effect is due to different normal force during advancing and receding of the particle. The normal force are changing, and at low compression, we have a chance to move. And then it depends on the tangential solution. And the motion we observe is similar to snake locomotion, but the structure is much simpler than this. This refers also to the way we walk when we start from the backward of our foot to the forward. So we have only two zones, stick zone in the center, in the middle, and slip zone on the periphery. And the interplay between those two gives us the motion we observe. Important part is to avoid jumping if we want to manipulate anything, because it leads to unstable behaviors which are hard to control. We can use our modeling results to optimize real systems by converting into physical quantities. Also, knowing X star and T star, we can compute the velocity of the drift. So we can see how efficient it is, and this could help to design optimal systems optimized systems. The experimental validation, well, there are two ongoing experiments. One is in Lille, conducted by PhD student Jules Gisquer. He has experiment on Rayleigh waves around a few megahertz to tens of megahertz. And it's his experiment that you've seen at the beginning. So yes, for him, there is drift against the wave. And I'm conducting experiment for Lamb waves. So it's another adaptation of this model for Lamb waves, which is a bit different, but still, and here, yeah, it's different system with a shaker. Yeah, for Jules, it's interdigital transducers and piezoelectric substrate that creates the wave. And for me, it's the shaker and a metallic plate, metallic beam. And I'm in the range of kilohertz, trying to move the particle. So the challenges for experiments to validate the model are plural. The first is that the model doesn't take into account tilting or rolling of the particle, and it must be axisymmetric. And actually, this is why you've seen these peculiar shapes of the particles on the video. One of them is hemisphere, which is hopefully rolls less than a sphere. Three spheres stuck together. It can be also cylinder or two cylinders stuck together. So yeah, then the second challenge is real waves. So we have reflections in reality from the edges of our substrate. And in the model, it's infinite, so there should be no reflection and the wave should be propagating and not standing. So we need to use some kind of absorbers to try to fight that. And also the amplitude distribution can be non-homogeneous, and then we will see more amplitude effects in reality than phase effect, which is the effect described by the model is phase effect, much weaker than the amplitude effects. So we must ensure that the amplitude is constant and homogeneous in the space we conduct the experiment. Third challenge is perpendicular motion. The model is two-dimensional and the world is three-dimensional, unfortunately. So either the third dimension perpendicular to the wave propagation should be taken into account, or some kind of restrictions like grooves or raised edges must apply, but it creates another friction forces or another tension if it's strings piercing a particle. So that's complicated. And the last one would be surface quality. The surface must be clean and no roughness. Otherwise, it changes the friction and the contact interaction between particle and the substrate. And I would like to thank you for your attention. And I would gladly answer your questions.
Well, thank you very much, Marina. Very interesting talk. So this way you can adjust, you can set conditions where the particles can move in one or the other direction. Are there any questions from the audience, attendees?
I have a question, if I can.
Olga.
Yes. I actually have three questions, but Marina partially answered one of them. One about the side drift. Yes, it's that the world is three-dimensional.
It's not taken into account.
It's not taken into account. But do you think if the model is extended, something useful could be, it could you could move your particle in different directions, or you can manipulate it in a little bit more interesting way, not just back and forwards.
Yes. Well, yes, that would be good, but it is complicated to take it into account. We don't know how to do that for the moment.
Okay.
Yeah.
And it's drift. Yes, I've already said that. And also on your diagram on the last slide, it's yes, on the right one there is this threshold value of amplitude and phase. You know, when the blue color becomes red one. Is it? Can you calculate the position, the coordinates of this point where the oscillations start?
Yeah, okay. There are analytical solutions for material point model. So for the left graph, yes, but for the right graph, I don't have an analytical solution. So this diagram is built completely numerical, point by point, and yeah. For the
But
moment,
still,
I don't have an analytical expression, but it is where sliding occurs. So it should be something similar to Coulomb's law. But yeah.
My last question about standing waves, because you mentioned that standing waves should be avoided.
Yes.
But again, it made me think that maybe something interesting could be achieved in terms of particle manipulation when you have this standing wave, just to explore the effect of reflections again too.
Actually, standing waves are exploited quite well, explored quite well. Yes, it's Chladni plates was experiment from 18th century,
yes,
and like there are jumping particles on the plates, and a group from Aalto University, they have videos. I didn't include them to avoid the confusion with my effect, but they can actually manipulate particles in both directions, like normal and tangential, and they can form letters or like patterns. It's slow jumping towards the node of the wave. So whenever they want to change the direction, they change the wave, they excite, and the node structure changes. And this is how they move for the standing waves. So yes, it's already done.
Okay, thank you. Thank you very much. That's all for me.
Thank you, Olga. Any other questions?
Sharon, there is a question on Q&A.
Oh, sorry. Yes, indeed.
Okay, what models do industrial companies currently use to find the frequency and amplitude for their chutes conveyors? Is it mainly from previous experience? I believe, yes, it's from previous experience, but again, my talk was mostly about like asymmetric friction, and for conveyors, it's asymmetric vibrations. So it's the angle between the wave that they excite and the conveyor that is important there. So yeah, I think it's mostly based on previous experience.
But surely current industrial conveyors, actually the conveyor moves as well, does it not?
Yes, it does.
And your work, one of the advantages is that different particles of different size or mass move in different directions given the same frequency. You can actually are able to separate.
Sorry, didn't hear you well. Can you repeat, please?
Sorry, I'm saying that one of the main points of this work, your work, is that you can separate particles of different size or mass move in different directions, and you're able to separate dry mixtures, which
it could be one of the applications. Yes.
that's right. Yeah.
I have a quick question.
Sure.
The model, the last model where deformability is accounted for, what effect of the material, what effect comes from, how big the effect from the material, so the Young's modulus?
I haven't studied like different diagrams, haven't plotted different diagrams for Young modulus yet. But I can say that if the Poisson ratios are equal between the material of a particle and the substrate, then the Young modulus doesn't matter at all. But if it's different, then it has to be taken into account, and what matters is the ratio between the Young modulus between particle and substrate, and not the absolute value of it. Yes, but I think that it shouldn't be that great. We studied that like the theta, the parameter in the model, I think it varies between like we tried quite large range of Young moduli for different materials, and I believe it varies like between 1 to 1.5, this theta variable. Well, and then yes, you have to build the diagrams, but I don't think it changes a lot. Maybe friction coefficient is more important in this problem. Yes.
And U here is so one nu is for the substrate which vibrates, and then one nu is for the particle nu p.
Yes.
So if substrate becomes non-deformable, well, just ideal case, then you are. Sorry, it can because you vibrated. Sorry, silly question. No.
It is deformable.
Yes, yes, indeed, yes.
Here, yes.
Okay. Any more questions? If not, then, well, I believe it remains to thank you, Dr. Terzi, for a very interesting talk. And thank you, our attendees, for joining us in this session. Thank you very much.
Thank you for having me.
You're welcome anytime, and hope you join us for in our future talks. Thank you.
Bye.
Bye-bye.
Thank you. Bye.
So I shall stop the recording.